Hi, everybody, and thank you for coming to this. This next session, linking metal biogeochemical cycling from the atomic to the landscape scale, is a great segue from what has just been talked about. Although as not the intended moderator, I was very happy to be asked to step in because this topic, in my opinion, is one of mineralogy's most fascinating and societally important subfields. So when we are asked, what good is mineralogy in the 21st century by non-scientists who think that being a mineralogist just involves looking at hand samples of quartz, or other people in our own departments, hydrogeologists and geophysicists, I'm going to pick on them, who mainly remember looking for 2Vs under the optical microscope when they were undergrads. And one of the things that we can say is that the following two talks will allow us to best convince the public that nanomineralogy is a critical component of our lives. So, first, I would like to introduce David Singer. He's from Kent State University, from atoms to mountains, new frontiers in X-ray science, and after that, Michael Schindler from Laurentian University, who will be talking about nanomineralogy, a new dimension to understand the fate of metalloids in the environment. And again, we will not have questions after the first talk. We'll save it for the discussion. Thank you.
Thank you very much for the invitation. I'm especially honored as a German Canadian to talk today about nanomineralogy for the MSA Centennial conference. And because it's such a special occasion, I thought I should dedicate my talk to my former PhD supervisor, Werner Bauer. Werner worked a lot with the crystal chemistry of silicate, phosphates, and sulfate, and wrote really interesting and fundamental paper about the crystal chemistry. And he was not only a great scientist and a good mentor, he told me also a lot of interesting stories about crystallography and crystal chemistry and mineralogy. And one story that somehow reminded my function as a nanomineralogist in environmental science, I want to share with you. So accordingly to Werner, Martin J. Berger at MIT introduced the R value to a crystal structure refinement in the late 50s, starting of the 60s. But this was not really well accepted throughout the world. In Germany, for example, they had for Martin J. Berger and his students a nickname. They called them the R-Sinnigen, which is a mixture of Wahnsinnigen, the German word for the crazy ones, and R value. And as we all know, the R value was finally then accepted. One reason why this was accepted, that students of Martin J. Berger went to other schools. So, for example, a postdoc of Martin Berger was Josef Siemann, an Austrian mineralogist, and he went to Göttingen, to the famous mineralogical department in Göttingen, and he was then the supervisor of Werner Bauer. And so they had already two R-Sinnigen, and so more and more R-Sinnigen came alive. And the analogy to my research is that I sometimes feel to be a nano-Sinnigen because I do nanomineralogy in environmental science, and I feel somehow not really well introduced yet. It's still an orphancy in my opinion. So what is nanomineralogy? So I came here up with my own definition. So we have already done traditionally nanomineralogy. We worked with clay minerals. We looked at structural features in minerals. With the introduction of the atomic force microscopy in the 90s, we looked at growth and dissolution features. And there was always a search for nano-inclusions. Every time a chemical analysis didn't make any sense, obviously we had to consider nano-inclusions in minerals. Now, Mike talked already quite a bit about new aspects of nanomineralogy. We look now at the chemical composition, structure, and physical property of incidental and engineering nanoparticles. And David and me, we look at mineralogical processes in nanometer-sized pore spaces. Now, I want to talk today especially only about those mineralogical processes in those nanometer-sized pore spaces. Those pore spaces are commonly referred to as confined pore spaces, as their small dimension limit the mass exchange with the environment. So I want to start talking first of why do we need to understand mineralogical processes in confined pore spaces. Then what are some of the intriguing properties of confined pore spaces. And then when you characterize mineral assemblage in confined pore space, you have to always expect unexpected mineralogy. So you're diving literally in an unexpected world. So why do we need to understand confined pore space? David has already shown this slideshow or this figure where we have a lot of little nanomineralogical or nano-confined pore space mineral surface coating, but also within grains. And those pore spaces on those nanometer confined pore spaces make up a large volume of surface area, a large fraction, and thus can strongly affect the fate of contaminants in the environment. Okay, so where do we find nano-confinements in the environment? So this is a paper from Penn from 2001, and she showed here coatings on quartz grains, and they appear all brownish. One would think, oh, they're all composed of iron hydroxide, but they're actually complex aluminum silicate coatings with iron oxide inclusion shown here. And we have here, as you can imagine, quite a significant amount of confined pore spaces. You can also find pore spaces, confined pore spaces, when you look at mineralized organic matter. So this is a paper from 2017. And when you zoom in, you can imagine there's a lot of little confined pore spaces within those larger pores of the organic matter. You can also look at organic matter itself that has not so much mineralized. So you can imagine here that you have a lot of little confined pore spaces within the organic matter. You can also look at the surface of a bacteria. Here's a bacterium, and it's coated with different minerals. You can see this here, and you can see in here, we have here 100 nanometer scale. You can see in here small little pore spaces, confined pores along the surface of the bacterium. So what are some of the intriguing properties of confined pore spaces? When we take a mineral surface, we have here the surface atoms, and we have here the adhesion forces between water molecules and the surface atoms. And as we know that we have a highly ordered water molecules along the surface, and this ordering effect goes out, and we have less ordered water when we come to a further distance from the surface. So when we have here a pore space, and we have here, let's say, a diameter of 300 nanometer, we obviously observe a higher ordering degree of water in the outer part of the pore space, and in the interior, which is further away from the surface, we have a lower degree of ordering. So with this ordering degree, we get somehow a decrease in the dielectric constant of water, which means we have a decreasing ability of the water to isolate negative and positive charged ions in solution. So here's a slide summarizing what we so far know about the properties of water in confined pore spaces. So the smaller the pore space, the higher proportion of ordered water in the pore, the higher proportion of water that loses ability to isolate counter ions from each other. And obviously, because we are in a confinement, we have a lower diffusion rate of orders by several orders. So our working hypothesis when we look at those confined pore spaces is that the unique properties of water in the confined pore space must have an effect on nucleation rates and mechanisms of solids. It must have an effect on pH and redox condition. It must have also an effect on the mass exchange between pores or between pores and bulk fluids and bulk soils. So we assume that mineral formation and transformation, and I want to give you some example today, in confined pore space may not follow the thermodynamics of bulk fluids. So today I want to show you what kind of mineralogical processes occur in confined pore spaces which are relevant to the fate of metalloids in the environment. And I want to give you some example about certain types of crystal growth processes or mineral structures that occur more often in those pore spaces than others. Okay, so for this purpose, we did over 10 different nanomineralogical studies so far on altered surface of minerals, organic matter, as well as confinements in colloids. And I want to only focus today on altered surfaces. Now, altered surfaces are very heterogeneous, so we need a really site-specific extraction method to look at an area of interest. So for this purpose, we use the focused ion beam technology. So when you have here a mineral surface coating, you do first scanning electron microscopy and you pick an area of interest, and then you zoom in and you see here, for example, this interface, and you want to look now at this interface and the mineralogy of the confinements along this interface. So you mark your area that you want to look at, then you put a protective platinum glue on top, a little bit thicker, and then you sputter with gallium ions from both sides to create a trench, and you keep the protective area intact, and you continue to sputter until you already see here's the area of interest, here's the interface you want to look at, and you continue doing this, and then at the end you flip your sample around, you cut it off, and you mount it on a sample holder, and then with the gallium ions again, you are creating an electron transparent section for transmission electron microscopy. And those FIP sections allow then to look at the mineralogy of those confined pore spaces. So I want to start here, what kind of mineralogical processes occur in confined pore spaces in mineral surfaces, mineralized organic matter, and organic matter. So one of the case studies, the most interesting one, we did in Trail in British Columbia, that is down here. Trail sits on the Columbia River, and this has been smelting processes at a local smelter occurred for the lead zinc or from the cotonees since over 100 years. And the lead contents in this local soil was at one point so high that they actually had to test the children for the amount of lead in their blood. And so we sampled along the Columbia River here. Here's a smelter, and we sampled around here. The soils are quite acidic with a pH of 3.6, 3.7, and we have up to 17,000 milligram per kilogram lead and up to 4,000 milligram zinc. So we took a focused ion beam section from a mineral surface coating shown here. The section was taken from there, and we took a FIP section from confined pore spaces or long confined pore spaces in a mineralized organic matter. So the first thing we recognized is the aggregation of nanoparticles. So we have here a crystal of franklinite and zinc spinel, and we see here those nanoparticles, and we zoom in. We can actually see the anglesite nanoparticles aggregating and agglomerating. And when you zoom in, you can actually really nicely see how those aggregation processes follow. So we have here one nanoparticle of anglesites, and it merges with another one. Then you have 2, 3, and then 4 nanoparticles. So you can actually really observe the agglomeration of nanoparticles in those confined pore spaces. Here is a really impressive image. We have here an illite crystal in the mineral surface coating, and you can see here that those anglesite nanoparticles attached to the basal surface of the illite. Here nicely shown the sheet structures. So you have a lot, not only agglomeration, aggregation processes, but also attachment of nanoparticles to silicate surfaces. So what we see here is the mineral kinterite, it's a lead iron arsenate from the mineral of the alunite supergroup, and it occurs in an amorphous silica matrix shown here, and you see those nanodots here. And when we take a closer look, you can actually see those nanodots, most likely of this lead iron arsenates, diffusing through the silica layer and attaching to the surface of the growing kinterite mineral. So we have here, this process is called crystallization through particle attachment. We have here the growth of the mineral through the nucleation of nanoparticles and their attachment to the mineral surface. What we also observe is perfectly idiomorphic crystals of franklinite growing nicely within amorphous matrices, nicely idiomorphic. And when you take a look here, we have here a franklinite crystal, and it's perfectly grown, aligned to a mineralized organic matter. We have here in green is phosphor. So we have here the string of former organic material, and this spinel crystal has been perfectly aligned and grown along the organic string shown here. So to look at mineralogical processes in organic matter, we went from Trail to Timmins. Timmins is in the northern part of Ontario, which is quite not north, but it's north considered for many people in southern Ontario. So here we have the Kid Creek smelter site. That's actually the mine is the deepest base metal mine in the world. It's 2.9 kilometer deep, and it operated from 1980 to 2010. And we have here predominantly copper, iron, sulfide, chalcopyrite, pyrite, pyrrhotite, swalarite, and galena. So we went somewhere close to the mine in an area, forest area, highly organic, rich soil. And we have here up to 13,000 milligram per kilogram copper that was wind-blown particular matter from the mining site to the local soils. And we looked here at organic matter, and I showed already this image. We have here attached to the organic matter chalcopyrite, pyrite, pyrrhotites, particular matter. And we decided we want to look now at the confinements within the organic matter. So we took two FIP sections, one along the outer surface of the organic matter, which are already bright here, and one where we have a chalcopyrite grain embedded in organic matter, and we looked here at the interface. And what we see is we find a lot of nanoparticles, very often metallic copper shown here, metallic copper nanoparticles, the organic matter. And one is actually here, those are covellite nanoparticles. Now, when you work in the environmental science field, you sometimes don't recognize right away analogies to larger scales. And it took me a while to understand that we actually look here at a nano-supergene process. In a supergene ore deposit, we have here normally the primary minerals, the chalcopyrite, and then the chalcopyrite in the oxidized zone is oxidized and leached, and we have then some of the copper and sulfur leached back to below the water table where we have an enriched zone in covellite and metallic copper. And exactly the same procedure we see here. We have chalcopyrite, particular matter attached to organic matter, and then we have a supergene process and forming metallic copper and copper sulfide nanoparticles within the organic matter. So a really nice example how you get those nanoscale processes resembling actually larger scale processes or forming processes in the environment. Now the reduction of the copper occurs here not via bacteria, it occurs mainly by humic and fulvic acid. We have here oxidized and reduced zones, but the microorganisms have still a rule because they literally transform oxidized into reduced humic substances, and those are then reduce iron or copper from iron 3 to iron 2. Okay, so I showed now how nanoscale processes, mineralogical processes occur in confined pore spaces and altered surfaces, but you can also look at particular matter and how particular matter is altered. And for this reason, we went to the same soils, to the soils in Timmins, and we took a look at a lead zinc bearing glass grain, and you can already see here the alterations feature, which are dendritic dissolution features. We see here those dendritic dissolution features, and we took a FIP section along those dendritic dissolution features with those alteration halos shown here. And we have here the distribution of lead, silicon, iron, and you see here in the FIP section already those alteration halos, and when we zoom in, the first thing what we see those needles. But those needles are actually composed of zinc-rich magnetite macamite, and when I zoom in, you can actually really nicely see those elongated spinel-type zinc-rich magnetite macamite. So we see again spinel phases, which we would have not expected, especially not being elongated like this. And when we also zoom in, we see here those nanoparticles, the aggregation of those nanoparticles, and we actually identified them as minium, as a lead spinel, and when we zoom in, we can actually see how those nanoparticles attach to each other and aggregate. So what are my summaries here regarding mineralogical processes? What are the most common mineralogical or crystal growth processes we have so far observed in confined pore spaces. So one of the most common feature is that we observe incidental nanoparticles. I mean, you would say, okay, there are nano-confined pore spaces, obviously there has to be nanoparticles, but what we didn't expect is that we see those nanoparticles, that they aggregate, that they agglomerate, that they attach to mineral surface, or that they actually are involved in crystal growth processes. We see a lot of spinel groups formed at low temperature. That was really a surprising feature, and we still haven't really understood how they form and why they form. And because normally you would expect that they are forming at high temperature processes, but we see them all at nanophases within those confined pore spaces. And obviously, because we are in confined pore spaces, we see a lot of minerals that are actually thermodynamically unfavorable when you consider that we only collected soils in the upper 5 centimeter of a soil. So we find metallic copper and covellite in the first top 5 centimeter of a soil. They're not supposed to be there. Or we find jarosite, a very acidic iron sulfate, in soils that are near neutral pH conditions. So there's many minerals that we not expect. And so what are my outlooks? Now, there's a lot to discover about mineralogy in confined pore spaces, a lot of things we don't know yet how those minerals form. But it's not only minerals that form in confined pore spaces. So for example, Manas et al. Showed here that you can actually synthesize amino acids in confined pore spaces. Here this is an iron-rich saponite, and here the authors basically argues that the high reactivity of those confined pore spaces allow the synthesis of those amino acids in those confinements. So there's a lot of discussers, a lot of little treasures, unknown mineralogy we can still look after. So I finally want to say thank you to the Nano Earth program, because a lot of my studies have been done at Virginia Tech, the Manitoba Institute of Materials, and NSERC for financial support. Thank you.